Chapter 28, Problem 46. A metal wire is sliding along two rails as shown. This slidable metal wire carries a current and at the same time it's exposed to a uniform magnetic field. It starts from rest and at 61.1 milliseconds we need to find out its velocity and its direction of motion. My first thought is any charge moving in a magnetic field feels a force. Current flowing through a wire represents many moving charges. So these many moving charges in a magnetic field means the wire carrying these moving charges, also known as current, is going to feel a force. Step 3, we derived this expression F equals IL cross B. This is a direct descendant of F equals QV cross B. Again, we just have a whole bunch of charges moving instead of just a single charge. Step 4, I'm going to go to the magnitude angle version of the cross product. Theta refers to the angle between the two neighbors, in this case the vector L and the vector B. So the question is, what's the angle between vector L and vector B? Vector L is a length vector. Its magnitude corresponds to the length of the wire and its direction is set by the direction of the current going through it. Make sure you see it and make sure you're satisfied that the angle between the L vector and the B vector is 90 degrees. Number 5, sine theta equals sine 90 equals 1. So F equals ILB, and Newton's second law says that in general F equals ma. So I have an expression for the acceleration of the wire. I know this is a kinematic situation, and number 6 is asking if this is a variable or constant acceleration kinematics situation. I'll go back to step 5 for a minute and I can see that the expression for acceleration is made up of terms that are all constant, so I can use constant acceleration kinematics. Step 7, I'm playing the big 5 game. There is the kinematics expression that contains the variable I'm after, which in this case is the final velocity, and all other variables are known. Step 8, part B is asking about the direction of the velocity at this time. This is a job for flat hand, right hand rule. Make sure your right hand is flat. Point your fingers upward because your fingers need to be aligned with the direction of the magnetic field. Your thumb always points in the direction of the charge velocity, which in this case the charge velocity is the current direction. So with your fingers pointing up and your thumb pointing in the current direction, your palm is facing leftward. So the magnetic force is oriented leftward, which means the acceleration is going to push this bar to the left. I'm summarizing this in step 9 and also specifying in terms of unit vectors.